Welcome everyone to this technical webinar. This webinar will be 1.5 hours or thereabouts. We have incorporated 2 to 3 worked examples due to demand or feedback that you guys wanted to see more practical implementation, and so we're doing that. We will model a cable and we will model a couple of tricky installations using FEM. And this will be a more or less purely technical presentation where you should learn quite a bit, and there's quite a lot of technical content to go through. And we will break it up with the examples. So who is ELEK Software? Well, we are a software development company based in Sydney, Australia. We have been building software for electrical power engineering and design since 2009. We support more than 10,000 users in more than 70 countries internationally. We have 3 main software products: ELEK Cable Pro Web for low voltage electrical system design, ELEK SafeGrid Earthing for custom earthing system design, and ELEK Cable High Voltage for cable rating, cable ampacity calculations. We serve customers from very, very large multinationals through to consultants, educational institutions, government organizations, etc. You can see part of the team there based in Sydney on one of our outings, but we have quite a bit larger team that's based in Australia and also internationally, an international team. Here's the high-level contents of the presentation. So I will talk about IEC 60287, current rating calculations and their limitation, finite element analysis for cable ratings and its advantages, how you can combine IEC with FEM calculations, meshing of objects, boundary conditions and sheath bonding, cable modeling guidance with an example using software, IEC versus FEM current ratings, which is very interesting and perhaps a little bit surprising for some of you. FEM for complex installations, that's where it really shines, the FEM method. Soil drying around cables and how that's incorporated into the FEM method. When to use IEC 60287 or FEM calculations, how to decide, and how air convection modeling is handled inside ducts using FEM. And then there'll be 2 live software demos, hopefully. Hopefully Edston will help us with that. Some interesting, challenging installations that you can only calculate using FEM, including multiple casings, so ducts inside a pipe, and cables in ducts in a backfill with a road surface. I'll conclude with and we will have a Q&A session where we answer your questions. So please keep typing your questions throughout the presentation into the chat. Probably Edston will answer a few of you, and he'll probably collect some of the questions for the end, those that we can't get through during the presentation. While Edston is demonstrating, I will also answer your questions in the chat, so please keep typing them as we go. ELEK Cable HV software is the software being used throughout the presentation where there is modeling or calculations. This software has a lot of capability, including the Finite Element Method. You can see along the top there are various methods that it covers, including FEM, where the IEC is limited generally. And then there are a bunch of modules, including short circuits, transient fields, and cable crossings. So that software is accurate and validated, intended for cable current rating calculations. It's suitable for any AC voltage and HVDC cables, complies with IEC standards, as well as being validated with CIGRE technical brochures, and it also has many of the CIGRE methods implemented. And we also have various ELEK methods where we have implemented methodologies and calculations that go beyond the IEC limitations, the IEC standards that we have developed through our own research and development. Like I said, this software is fully validated with CIGRE Technical Brochure 880. You can get a free trial of the software if you visit elek.com and just go to the software drop-down menu. IEC 60287 current rating calculations is the penultimate standard for providing analytical equations for cable current ratings. This standard is regarded as accurate and still widely in use because it is adaptable for common cable types, still in use these days, and is common installation methods. It's regarded as still being reasonably accurate, which leads to reliable and consistent and comparable current rating calculations and results for various stakeholders involved in high voltage cable projects. The IEC standard calculations are somewhat complicated to implement and ambiguous in parts. There are 9 parts to the standard in total, and of which we have implemented. But like I said, it's ambiguous in parts, and that's where the CIGRE brochures help with that. So how do you validate your cable current rating calculations to IEC 60287? Well, you can use the benchmark examples in CIGRE TB 880. There are 11 benchmark examples or 17 calculations with 49 guidance points. The purpose of this document is that you can validate or perform verification of your calculation tools, which we have done. We have complete matching results with all of the case studies up to the maximum accuracy of 11 decimal places. Accurate armor loss calculations. This is also a very important factor when performing these calculations. There is another technical brochure, CIGRE Technical Brochure 908, released in 2023, which provides analytical equations and also some FEM-based approaches to how you should consider magnetic armor losses in 3-core armored cables. And we have implemented these methods within our software. There's another technical brochure, which is more recent, very, very recent, CIGRE Technical Brochure 963, which does cover the finite element analysis for cable ratings. We've been involved in looking at that technical brochure for some time. It provides formal guidance on how you can perform FEM calculations for cable ratings. It's more of a general guide, so it provides guidance points. It doesn't provide you specifics, and it's more aimed at those wanting to perform these calculations using like general FEM software, setting up your own custom models, modeling cables using these general tools, which in our experience is very, very time consuming. So it's quite a bit different to how you would need to do it in our software. So we automate all of the model setup and the meshing and everything like that in our software. We make it as easy as doing an IEC calculation to perform FEM in ELEK software. We have validated our software against these results given in this technical brochure, and we have very close results with their case studies. So what are the problems with IEC 60287 calculations? This standard makes assumptions in the external thermal resistance calculations that are often inaccurate, inflexible, and limiting. The analytical equations of IEC 60287 are limited to the assumptions that the ground surface is isothermal when it is not. The cable surface is isothermal when it also is not. The superposition principle applies for mutual heating when it generally does not, especially for cables that are close or touching. But although the IEC 60287 does have separate equations for touching cables, they are nowhere near as accurate as FEM. And in 2016, there was a research and development project undertaken over a few years by National Grid in the United Kingdom, which is the main utility there, that advised that the final finding of that investigation was that the isothermal ground surface assumption of the IEC calculations result in overrating for cables. So optimistic ratings for cables that are buried shallower than 1 meter. We think it's a bit deeper than that. That's what we've found, including those installed in surface troughs. So the IEC 60287 calculations are giving optimistic ratings for cables, for buried cables compared to FEM. And we'll show you that later. So what are some of the advantages of FEM? They include that any HV cable installation and configuration can be modeled. your exact installation condition. This leads to better accuracy. For example, FEM can model multiple zones of varying soil thermal resistivity. This can't be done using IEC 60287 equations or methods directly. You must use FEM. So on the left-hand side, you can see a model setup, a cross-section of an installation consisting of multiple HV cables in separate backfills, and even a filled trough with 3-core cables in a duct. For example, on the right-hand side, you'll see a typical installation like this with multi-layered soils, multiple zones of different thermal resistivity, multiple circuits. And this is actually an FEM mesh plot, which is synonymous with the finite element method. Continuing with the advantages of FEM, FEM can model the heat transfer between the ground surface and the air. That's not in the IEC method. It is assumed that there is no heat is transferred between the ground surface and the air above, which is known as the isothermal assumption. FEM allows the convection of heat generated by the buried cables, which flows into the ambient air to be considered. So when you perform an FEM calculation, and you use a non-isothermal ground surface calculation, in our software you can use either, you'll be asked for the ambient air temperature, and that affects the convection or the heat transfer between the ground surface, which is produced by the buried cables, and the air itself. Also, mutual heating is handled very differently in FEM compared to the IEC 60287 calculations. Mutual heating effects of cables is more accurate in FEM, especially for touching cables or cables that are nearby. With FEM, the mutual heat flux influence and disturbance are considered simultaneously, whereas in the IEC method, the simple superposition theorem is used for mutual heating between cables. But with FEM, on the right-hand side, you'll see this typical mesh plot. And at every single node of that mesh, we calculate the temperature, and that mesh, the fineness of the mesh is more intense around the cables, or where there are transitions between different materials. That's where we apply a very fine mesh, and we calculate lots of temperatures to give an accurate profile and ultimately an accurate current rating calculation. So what if you could combine the IEC 60287 calculations with FEM? That's what we've done. So you can combine the thermal resistivity approach. So everything within the cable T1 to T3 can be calculated using IEC. Then all of the electrical losses related to the bonding, etc., and the electrical losses of the conductor are performed using the IEC equations. And then everything external to the cable is modeled more accurately using the finite element technique. That includes any air gaps between the cable and a duct, and any sort of external thermal environments. We use the IEC for calculating the current rating, as you can see on the bottom of the slide. So the FEM algorithm is fully iterative. It's automated. Here's a high-level overview of how we handle the calculations. So first up, we look at the model and we organize the objects into a hierarchy, starting with the cables and the external thermal environment, be that different backfills, etc. We need to know the hierarchy of the layers, and we organize that in code. Then we assign electrical losses to the metallic cable components, which depends on the bonding. We also assign thermal properties to the cable components and the environment objects. So what I've just mentioned to you, including the cable layers, if you're using a FEM package, you have to do this manually for every different type of cable, every installation. That's why with a general software, it can take you hours or days to set these models up. With our FEM package, this is all automatically done within seconds. We subdivide, step number 4, we subdivide the 2D model space into smaller parts. This is known as the meshing. This is all fully automated. The mesh is fully automatic. And then we solve the large system of equations for all the node temperatures in the model, as I mentioned before. And once we know all of the temperatures, you can see in the image here a mesh plot zoomed in. So you've got the cable, the different layers, the wires in the cable. We mesh all of those, and at the intersections between the different layers, we mesh even finer. And because we need to understand all of the temperatures extremely well, especially between the transitions of material types, which almost always do have different thermal resistivities. So with that information of temperatures, we can accurately calculate the current carrying capacity of the cables in the model. So how do we mesh the objects? So you can see some more examples here. The meshing is fully automated. We triangulate or discretize the environment. We subdivide the domain into a network of triangles. It's performed individually on each cable layer or component within the cable, as well as the environment. You can see a duct here is being meshed. You can see in the bottom right-hand corner, you've got a close-up of a HVDC cable with a double Armour. So you can see the two purple rings on that model, the double Armour of the cable being modeled and also being meshed quite finely. Now, finer meshes in general lead to more accurate result, you could say. We understand that it's most important to have a very fine mesh at the transitions between different materials. And this is generally understood by FEM experts. If you mesh too finely, that could compromise speed of the calculations. These calculations do take time, whereas a pure IEC calculation will be almost instant, even though it's iterative. But these FEM calculations, because they involve calculating millions of temperature points, can take minutes, sometimes longer than that if it's a very complicated model. Also, the boundary and the boundary conditions are also important. So in the bottom right-hand corner, you'll see that this FEM boundary, it needs to end somewhere. It needs to extend to somewhere, and it needs to end somewhere. So you need to mesh, and you can't see the cables in this model, but there are cables there. You can see this environment extends up to 300 meters. In this case, 150 meters either side of the cable. We choose that automatically. And also we need to go very deep. So on both sides of the model and the bottom face, we need to have conditions where there is no or zero heat flux at those locations. And that's where the model ends. That's the boundary conditions for the sides and the bottom of the model. And then the top face, or the top boundary, I should say, is for buried installations, is the interface between the ground surface and the air environment. That's a different kind of boundary condition. It could be isothermal or non-isothermal. Where non-isothermal involves heat transfer and convection by air, which is complicated. So heat transfer from the cables into the air above. And you can see that even at the edges around this boundary, we need to apply quite a fine mesh. Let's just mention sheath bonding because it's a very important factor. It's all incorporated within the FEM calculations. It's actually one of the more complicated things to model when you're doing FEM, especially if you're using general FEM software. To incorporate the electrical losses caused by the bonding is very complicated and very time consuming. I wouldn't recommend it. And we'll cover why and what CIGRE says about that as well. So if the cables are solidly bonded, you could expect electrical losses in the sheath of between 20 to 40%. You also have single point bonded cables, but you need to take care or carefully manage to prevent sheath over voltages. That needs to be in the calculation as well. And if you're using cross bonding, that's also a little bit more complicated. The system is more costly because of the complication, but ultimately that leads to cancellation of induced voltages, smaller currents on the sheath, which leads to increased current capacity of the cables. We have standardized equations and incorporated all these bonding types and a few variations of those within our FEM calculations, which is very important, as I said, and adds quite a bit of complexity. Here's an example of a cable that is solidly bonded. I realize a 400 kV cable wouldn't be solidly bonded in real life, but It applies to any voltage of cables. So we've got 3 phases touching in trefoil arrangement. You can see that the sheath circulating current is quite significant, and that will almost always be the case where you're using a solidly bonded sheath. You'll have high circulating currents in the sheath, and that leads to additional heating in the cable, which reduces its current carrying capacity of the main conductor. You can see in this case that the electrical losses are quite significant in the sheath, which is of a corrugated aluminium type. We'll talk about cable modeling briefly because it's an important stage in any current capacity calculation. And then I'll hand over to Edston, who will briefly give us an example of how to model a custom cable using a software package. And then we'll continue with quite a bit more technical content and then the other examples. So when you're modeling a cable to get its current capacity, you should use the manufacturer data sheet that should be obtained. Ideally, I should also mention, if you can't do that initially, at least, we have a huge database of our software that we're continually adding to, thousands of cables now of all voltage levels, from mainly adhering to IEC standards, but we also have some cables in the database too. You should reference IEC standards and CIGRE guides for material properties, so the thermal resistivity constants. But if you're using a software package like ours, all of those material constants are already inbuilt, and you can use custom material types and enter custom material properties if you have different information. You should follow guidance from CIGRE TB880 about modeling cables. For example, that includes prioritizing the diameter over thicknesses in cable data sheets. Edston will show you why. And you should avoid combining layers of different materials in a cable model. You should create custom layers for those. There's an example on the screen of a cable manufacturer data sheet. That's a submarine 3-core cable, quite a complicated cable. You can model that. Well, you should model any sort of cable that you want to know the current capacity of with quite a good accuracy. I'll hand over to Edston, who will do a demonstration of how to model a cable from a data sheet. Whoops. So let me just hand over. Thanks, Edston. Take it away.
Okay, hope my screen is visible, Jayson.
Yep.
Okay, so hi everyone. So we will be trying to model this cable model from TB880. This is a 132 kV cable with a millican conductor and a 1200 square copper conductor. Let's see how we can do it in the software and how easily we can do it in the software. As Jayson pointed out, in our software we have a list of cables which you can pick from our database. We have around a large number of cables from different manufacturers as well as other cables. And these are the lists that you can see on my screen. So you can use any of these cables, or if required, we can model our own cable. So how do we do that is what we are going to see now. So we start from scratch. Let's start from a new cable model. Okay, so the first thing we do is try to write a description for the cable. Let's just generally call it 132 kV cable. Now we see that this cable is an extruded cable. So we have the cable type of extruded. There are many other options such as HVDC or pipe type, submarine, triplex cables, etc. So for this example, I'm using the extruded cable. It's a single core cable. It's a 3-phase cable. The phase to phase voltage is 132 kilovolt, 50 hertz normally being used. There are measurement units. If you have units in metric, you can shift them from metric to imperial, whichever standard you follow. For this study, we will keep it in metric because all these units are in metric. So these are the general settings. Next, we go to our conductor. Now the conductor specified here is a millican compacted copper bare wire bidirectional, which has some water block layers. And the thickness of the conductor is 43.1 mm. So let me enter that here, 0.1 mm. The size of the conductor is 1200 square mm. It's specified at the top here, the blue column. It's copper wires, and the cable and the conductor is a millican bidirectional, so we can pick it up from this option. This conductor type decides your skin effect and proximity effect coefficient, so that's why that's very important to pick it up. The resistance at 20 degrees for this conductor is 0.0151 ohms per kilometer. If you look at the electrical data at the bottom of the table, we will see that the resistance is matched up. So this is one way to look at whether the conductor has been specified properly. The next layer that we're going to see is a connector screen. It's a semi-conducting tape with a semi-conducting compound. The diameter is 46.7 mm. So we have a list of standard layers on the left hand side. You can add a conductor screen from there. The diameter is going to be 46.7. It's a semi-conducting tape, so it's extruded semiconductor material. If it's not, you can have your custom material and enter all the parameters that is required. But for this example, we will leave it at extruded semiconductor. The next one is an insulation, which is XLPE. So I can go to the insulation. Now, XLPE, if you look at the drop downs that we have here for XLPE, we have a few options of insulations here. Many XLPs are there. So you should be careful which XLP you choose to. Normally it's a XLP which is greater than 36 kilovolt because of the voltage of the cable, but we have filled and unfilled here. But as per TB 880, if it's not specified whether it is filled, you always use the unfilled option. So because the cable datasheet gives us only XLP, I'm going with an unfilled option. So I select that. Now, the dimensions of the screen of the insulation, if you look here, it says the thickness is 16.1 and the diameter is 80.5. So if I type in 80.5, the thickness is calculated and the thickness is 16.9 and not 16.1. As per the suggestion from TB880, we always prioritize the diameters and not the thicknesses. So this 16.1 thickness, which is in the datasheet, is omitted, it's discarded, and we go with 80.5, which is the diameter of the insulation. The insulation capacitance either can be calculated or you can specify it if you know the value. Normally we leave it as calculated. So each the loss factors and the thermal residues are pre-populated depending on the value you select. But if you have another custom values, you are free to, you can enter them in these in this area. The next element we have is an insulation screen. The insulation screen is again a semiconducting compound. So I can add an insulation screen here. The diameter of the insulation screen is 82.9. So I can edit this. The thickness is automatically calculated as 1.2. It's again a semiconducting compound. So I can leave it as semiconductor, extruded semiconducting compound. The next element here is an earthing screen. The screen is copper round wires with a counter helix of copper tape. Now, again, TB880 suggests that if there's a counter helix of copper tape over the wires, you can avoid them in calculation. So that's what we are going to do. So let's model this copper round wires. So screen, and before that, there is a bedding layer, which is a semiconducting swellable tape. This is like a water blocking tape here. So let's add that. Now those layers are not specified here. They are custom layers to be added. So we can insert a custom layer here after the insulation screen. So this is my custom layer. I can call it as bedding 1. The diameter of the bedding is 84.3. So I can specify that. Now the thermal resistance of this bedding layer, we have lots of materials here with all pre-populated properties. This example use a water blocking tape. So we can select that. It has a high thermal resistivity of 12. And so we are selecting that. So if there are some other materials, you can select it depending on the drop down, or you could have custom materials as well. And next one is the screen that we talked about earlier. Okay, so the screen is copper round wires. So the material is copper. The construction is round wires. The diameter of the screen is 87.8. So 87.8. Now again, if you see for the screen, the diameter of the wire specified is 1.77 mm, but we are able to reach only 1.75. That is because we are trying to prioritize the diameters. The number of wires specified here is 57. So I can enter 57. The other important parameter is lay length. Lay length is 500 mm. So lay length is the coverage of the wire around the core. So it's about 500 mm. So I can input lay length as 500 mm. So that completes the screen design. The next one is another bedding layer. So we can add another custom layer. I can call it as bedding 2. The diameter is 88.4. So 88.4. Again, I assume it to be a water blocking tape because it's a water block tape, and the values are populated here. Now after that, we have a sheath, which is the aluminium foil. So I have a sheath layer here. I can add the sheath layer. Now the sheath layer is an aluminium foil. So from the material, I can select aluminium. The thickness is 88.8. So I can enter 88.8 here. And the DC resistance and the area of coverage, everything will be displayed as we change the values. The next layer is an outer sheath. We can either use a custom material or you can use a jacket. So let me use a jacket here. Now the outer sheath is a polyethylene jacket. So it's polyethylene. You have those materials here. Let me select polyethylene. And the diameter is 97. And then we have the thermal resistivity as T.5 for polyethylene. And the last layer is an outer semiconductive coating. It is 98 mm. So I can add a custom material layer. I can call it as a semiconductive coating and the diameter is 98 and we have all the properties here. So once we generate this cable model, we can save this and use it for all our projects. And once we exit this, we get the settings of the cable models where you can enter the bonding, the temperature limits, etc. Can be entered here. So this is how we model a cable in Cable HV.
Thank you so
Thanks.
much, Edston. Okay, I'll take it from here. So I will continue through some more technical slides, and then we will have a couple of more demonstrations of modeling. So here's an interesting comparison for a typical installation, typical scenario where the ratings are calculated using a pure IEC approach are compared with the FEM method. So it's a little bit surprising for some in that the ratings given by the FEM method are lower than the IEC method, particularly where you are using a non-isothermal ground surface, so considering convection above the ground, especially for shallow burials, shallow buried cables. So you can see as burial depth increases, especially for the isothermal method, the ratings will converge. But again, you'll see this that the IEC, a pure IEC calculation, gives optimistic current ratings compared to the FEM. And FEM is regarded as being more accurate, but it gives lower ratings in general. So FEM can deal with complex installation, such as what you can see here, where you can configure or consider a non-isothermal ground surface with air temperature and convection above the ground surface. We perform an iterative calculation for the ground surface heat transfer where we iterate for the convection coefficient H. You can see in this example, you've got multiple zones of different thermal resistivity. You've got your mesh plot and you've got a soil temperature plot. You've got multiple buried touching cables. They can be any number of circuits. You can consider them as equally loaded or non-equally loaded. We can also perform transient rating calculations on this installation as well. Here's another example of a complex installation, which is a very large steel casing. This has been modeled in our software. You certainly can't get an accurate result for this installation using a pure IEC approach. This would represent a large steel casing for a traverse under a roadway perhaps, or a railway or a river or a sea. And on the right hand side, you'll see the FEM mesh plot combined with a temperature plot. And if you look at the model closely, all of the different circuits will have a different rating because their temperature distribution is different. You've got ducts filled with air. You've got the steel pipe filled with some sort of material which has a thermal resistivity. And all of the mutual heating can be calculated using FEM. Multiple circuit calculations. FEM does a better job than IEC at this. You can have a single backfill or multiple backfills. So the heat transfer between the cables, especially touching cables, is quite complicated. FEM performs better. It gives better results than IEC-based mutual heating calculations. You could consider that the cables in our software we term isolated ratings where mutual heating is ignored, equally loaded circuits or non-equally loaded. The equally loaded situation or algorithm requires more iterations than an unequally loaded calculation, but it depends on your situation. Here's a very brief example of where modeling HV cables, for example, at a wind farm landfall, would require FEM. So in the bottom right-hand corner, you've got multiple export cables within a pipe, and this certainly requires the use of FEM to do an accurate calculation. You can't use an IEC-based approach for that thermal calculation. Here's an example where IEC also can go wrong, where FEM proves this. So there are assumptions with the IEC method, particularly with particularly where in this case where a backfill is involved. There are assumptions around that backfill calculation, simplified backfill calculations of the IEC method that assume that the cables within the backfill are a single heat source that is located at the center of the backfill. Now, if you have this sort of vertical arrangement within a backfill, the IEC calculations go very wrong. So in this example, what we've done is we've fixed the loaded current, and there's two circuits here, two three-phase circuits, one on the left, vertically arranged, and one on the right, and we've fixed the currents. So the two circuits have carrying very different currents. So there's an imbalance of heating within the backfill, and then we've calculated temperature, and FEM gives a very different temperature than IEC, and you should consider that in this case that the IEC thermal calculation gets it wrong and can lead to overestimated temperatures in this case that are incorrect. Oops. Some other examples where you need to use FEM, so multiple zones of different thermal resistivity in this solar application, where on the left-hand side, you've got multiple DC circuits in one trench, and then adjacent to that or nearby, you've got multiple medium voltage cables. You can see in the bottom left-hand corner, you've got your mesh plot. In the top right-hand corner, you've got your simple DC cable models that operate at quite a high conductor temperature. And then in the bottom right-hand corner, if you need to consider cyclic ratings, you can apply that calculation also to optimize the ratings. Soil drying around cables is very important to consider where it could happen. How does it work? Well, the heat from cables may cause significant moisture migration away from the cables. The main cause is the temperature gradient within the soil. A dry out zone may develop around the cables, especially outside of the backfill, which is generally thermally controllable. There is a sharp transition from low thermal resistivity to high as drying occurs, and moisture migration can occur. Moisture migration is complicated. It's a dynamic process that is extremely complicated. In general, we use a two-zone approximation of this phenomenon, including in FEM, and I'll show you how we implement that in FEM. But the IEC 60287 calculations are really quite limited in terms of soil drying. The limitations include that you can only consider a single or isolated cable or a single circuit. You can't apply soil drying to multiple buried circuits. ELEK has in fact extended this limitation to allow the of soil drying for multiple buried circuits. That's a world first actually. So you can do that in our software, but in general, it's a limitation of IEC. Also, you can only apply soil drying to unity load factor. We don't have that limitation either. And it only applies to direct buried cables at standard burial depths. All of those assumptions, we have actually extended those limitations, but in general, they are a limitation, and there are more considerations there's a different approach required for FEM. But in general, in the bottom right-hand corner, you'll see the image, the cross-section of a backfill, a trench with lots of buried circuits in ducts. If you wanted to incorporate soil drying considerations within that model, you couldn't do that using a pure IEC approach. So that's where either an extended approach or the FEM method comes into play. To consider soil drying in FEM calculations, we apply this drying out function, a smooth drying out function that applies this two-zone approach. So what you do is you define the temperature, the critical temperature at which soil drying occurs, and you define the native or moist soil TR, thermal resistivity, and the dry tier. And the software during the FEM calculation will apply this function to the soil according to the calculated temperatures. So if the temperature using FEM is calculated to be above the critical temperature, then it's considered dry, and we apply the higher tier to that zone. So when should you use IEC versus FEM? In general, you should use the standardized analytical IEC method for simple, well-defined cases to minimize effort and time according to the CIGRE technical brochure. We say that because our FEM is so fast and easy to set up, it's actually almost as fast as doing as an IEC calculation. We don't really agree with, it's not much effort, and it doesn't take much more time to do FEM in our software. So you could make the decision on that, but it's not really going to take you much time in ELEK software. For complex scenarios, you should use FEM for heterogeneous soils, complex soil structures, large groups of cables, or when higher accuracy is needed and IEC methods are less applicable or not applicable. And this table contains some reasons for when you should use IEC or FEM, where there's complex scenarios or soil drying, etc. So you can use that as a reference. Air convection model inside the ducts. This is a big concern for our users, for those calculating current capacity, particularly for complex installations using the finite element method. You need to consider the air convection within the duct to a good degree, and that involves considering or applying a good convection model. So in general, when you've got air-filled ducts, you'll see this flow. You'll get this flow of air being heated, and in general, it flows up. Hot air flows up around the cable surface, and then once it reaches the inside of the duct, it cools down and it flows back down to the bottom of the duct, and it creates this circulating motion of air. It applies wherever the cable is located within the duct, be that at the bottom or in the center. In practical cases, the cables are generally at the bottom of the duct. This changes the convection as shown in the images here, and ultimately changes the current rating. But it's important to have this model implemented for your FEM calculations, such as we do. Oops. Multiple casings is also another interesting, challenging application requiring FEM calculations. That's where you've got cables in ducts within a pipe or an outer duct. You certainly can't do this calculation using a pure IEC approach. The application of this would be a directional driller installation. Now the ducts can be of any sort of material, so can be the casing may be plastic, or it may be or otherwise, and it can be filled with air or a pumpable material. Generally, it's filled with a pumpable material. The ducts may be filled also with a pumpable material, or there may be sections filled with air or even water. And so your model should be able to deal with that. Our FEM model can deal with any of these combinations. I think Edston will show you that within our software, and how to model a complex installation like this. But with FEM, you can even model multiple HDDs or these casing installations adjacent to each other, all the mutual heating. There's no real limitation. With FEM, you can model any number of layers of ducts, so ducts within pipes, all sorts of combinations. It's really not limited with FEM as it is with IEC. You should verify your calculations. We've done verification of this installation and many others. This is based on a CIGRE, and we have good agreements with this. This is more a simple pipe type installation, or I should say for directional drilling, really. Additional verification. There are some additional case studies that we've validated our FEM calculations, and we have very good agreements with the CIGRE case studies that are available in the latest technical brochure within a very small percentage. So you should, if you're doing FEM calculations, you should definitely validate your calculations with that technical brochure examples or ours or others. But our FEM calculations are validated. So I'll hand back to Edston, and he can show you how some of these FEM calculations using software. Please keep typing your questions in the chat. So his demonstration will be 15 to 20 minutes, I would say, and then we will go to a live Q&A. I will also give you a link to where you can get your fill out a form to get your certificate. So I'll hand over to Edston. Thanks, Edston.
My screen is visible.
Yeah.
Yeah. Okay. So what we are trying to do here is to show you an installation which is in TB963. Let me just bring up the document for your viewing. So this is the TB963 document which was released last month. So they have given a case study which is a cable in a duct in a backfill with an asphalt layer. So just to show you, so this is the installation, how it looks like. So the cables in this case are in the center of the duct. This was done because they wanted to verify this method with an IEC model that they have developed equivalent to the FEM. So for this case, we will try to keep the cable in the center of the duct, and then we will build a model around that. But in general cases, if it's air-filled, the cable will be at the bottom of the duct. But ELEK software has the capability to place the cable anywhere you want, so that we can verify these type of cases. So the cable model used in this example is cable model 0 from TB880. So I can open the cable model for you from our library. So all the TB80 cables are here. So it's a K0 cable. I can open that. It's a solidly bonded cable. So that is what is being used. Now let's see the installation conditions for all this. Now, as I told you, we will be trying to come up with a comparison with an IEC method. Because we are comparing with an IEC method, we would always keep the ground surface as isothermal. If not general FEM methods, we can use the non-isothermal soil boundaries. Now, the installation parameters are in here. The ambient surface ground temperature is 20 degrees and the soil thermal resistivity is 1. So let me change that here. Now, the cables, as I showed you, this is how the cables are. So we have 3 cables. They are spaced at 0.3 meter apart. So I have, and their depth is 1 meter. So I have my cable now at X 0.1 and Y 0.7. I can make it at 0 and 1. I want to make them spaced, so I would prefer the custom arrangement. So I will go to custom arrangement, and because they are 0.3 meters apart, I can type in 0.3 minus 0.30 and 0.3. So the cables have been set up as this image. The next thing is to add the duct. Now, if we look at the duct from here, all the duct parameters given here, the outer diameter, the thickness, etc. is given here. So let's go forward and do the ducts. Now, generally in cable HV, when you add a duct, the duct gets associated to the circuit. So if you see here, the duct is placed at the bottom of the circuit. But because I want the duct or the cable to be in the center of the duct, what I would do is I would remove those associations. So I will say that it is an empty casing. So now I've created an empty casing here. This empty casing, let me set all the parameters for it. So the center of the duct is minus 0.3, same as the cable, and the Y center is 1. The duct diameter specified is 140 millimeters, so I make it 140 mm. The inner diameter we have to calculate, but the duct thickness is 10.3. So when you do the calculation, you would get 119.4 mm. So this is one duct. Now let me finish off all the duct parameters. The filler of the duct is air here in this case. The duct filler material, we have lots of material, PVC, PE, etc. etc. I can use custom also here, but let me use custom here for the time being, but I'm using the same thermal resistivity as polyethylene, that is PE. So it doesn't make much of a difference. So now I've created one duct. Now I can copy this duct to the other cables also. So I just copy the duct and just change the positions. So 0 and 1 is my next position. And then again make another copy of it. And 0.3 and 1 is the next position. So I just copy all the ducts and all the ducts are formed here. So now I have done with the ducts. The next thing is to create a backfill, the small backfill which you see here around the cable. So the backfill is given by a duct bank, a width of 1. The height is 0.5, which is here. So what I do is I go to the backfill tab and I add a backfill. Now this backfill, you can drag it with your mouse and bring it wherever you want. But if you want precise, you can go back to the arrangements, make it 0 and 1. The centers are same here. The width of the backfill is 1. It is 1 here. That's a default value in cable HV. The height is 0.5 here. Same 0.5 here. And the backfill thermal resistivity, as per this screenshot, it is 0.5 Kelvin meter per watt. So let me change it to 0.5 Kelvin meter per watt. Now I can change this image to something else if you want to, just to make it a bit more colorful. The next thing I do is I have another layer of asphalt on top of it. This is like a road here. So the dimensions of this layer is given here. If you see, the asphalt layer height is 0.1 meter. But the width was not specified. But if you look at the image, it goes from -3 up to +3. So we assumed it's going to be a 6 meter asphalt layer. So what I do is I create another backfill here. This backfill, let me take the center is 0 itself. Let me take the width of backfill is 6 meters and the backfill height is 0.1 meters. Now, if I want it to touch the ground surface, I can just make the Y as 0. The software will adjust it and bring it just below the soil layer. So now I have the backfill layer just touching the soil layer. So that's why it's coming at 0.05 and the width is 6 meters and the backfill height is 0.1 meter. That's what it's told in this figure. Now I need to know the thermal resistivity of asphalt. As per this document, the thermal resistivity is 1.33. So I go ahead and do 1.33. I can again change it. I can decide if I think that these names for the ducts are too crowded here. I can go to the ducts. I can switch off all the names. So I don't want the name, my custom names also for the ducts. I can give backfill their own names, etc. etc. So just to make the figure a bit more appealing, I just removed all the names. So this is our setup now. Now we just go ahead and calculate. Keep in mind that cable HV has a calculate button only for the FEM module because it is a bit of time consuming process. Let me just remove all these things. Yeah, so if I just press calculate, I would expect a minute or something for this to happen in FEM. Yeah, I've done started the calculations for it. Now, as Jayson pointed out, we have selected the meshing area for this system to be around 300 meters on either side, or either side 150 meters, and the depth to be 200 meters. So that's a large area to cover. We expect more than 100,000 nodes in this setup. That's why we need a bit of
How
time to
many
calculate this
how many iterations do we expect for this calculation?
normally under 10.
Isothermal ground surface, so it should be
Yes, because
faster calculations, right?
yeah, because we want to compare it with the IEC method. So
Yeah,
that's what the document has done. So we'll also follow that.
with non-isothermal, right?
Yes, it'll be a bit slower because we will have to do iterations at the ground level to get the heat convection coefficient. So that will take a bit more time. But I think this should pretty fast finish by now. By 6 or 7 iterations, it should finish.
So it's performing all the meshing and doing iterations, right?
Yes, it performs, it does all the iterations, it gives me the current rating, it gives me all the losses, loss factors, the sheet circulating currents which are here, it gives you the sequence impedances, it gives you the short circuit currents, it will give you all the thermal resistances, T1, T2, T3, T4. It'll give you all the temperature of the components, conductor, jacket, and sheath. It gives you all the cable data, and then it gives you summary of results. Now, if you look at the document, yeah, so these are the results that I want to show you. Yeah, so this is the case one that we are seeing with the cables at the center of the duct, and we got 615 amperes is the rating. I'll just have a screenshot for you here. So we get, oh sorry, yeah, we have got around 613.97. It's very much close to 615. So this is how we validate our software with TB963. So this is a screenshot from TB963. So yeah, so this gives us a good agreement and a good understanding of the software as well. The 610 is because as per TB80 suggestion, they've asked us to round it down to the nearest tenth. So that's why it shows 610 here and the figure, but the actual current rating would be 613.97. I will show you the mesh plot in the next example probably. But again, the convergence tolerance are kept much lower here because we want to save time. But if you can go to higher convergence tolerances, probably you will come closer to the 650 number. But we think that's not necessary. One is good enough for an initial start. One is good enough.
Should we do a multiple casing case quickly, Edson?
Yeah, I'll do it quickly. There's another CIGRE document that is coming out. So now which we understand they'll deal with multiple casings and all, but just we'll show you how we can do multiple casings here. Again, I'll make it isothermal because I want to do it quickly here. So
Just in general, Edson, let's just do around
yeah,
the general.
let me do this case. So let me take this case. So there are cables are here. Let me just put it at just for 0 and 1. It's in triangular formation. I add ducts to it. So I add ducts. Let me just put it as 140 and 119.4. And so there are ducts associated with it. Now I want to add an additional duct to it. So let me add an additional duct. It's an empty casing. Let me drag it and put it here. Let me make it the same size as, just to avoid overlapping errors. And so the last duct is an empty duct. It's a spare duct. Now I can add one more duct which is a bit larger, encasing all the cables. If you want precise arrangements, we can use the controls on the left hand side. So this is how we make it. So easy to make it here. I can fill the ducts with a solid material, for example. I can fill the solid material. So now these three ducts are solid material. This is air, or if I go back to the larger duct, I can fill that also with solid material, and I just can proceed to calculations.
Yeah. This will also be reasonably fast, right?
Yeah, it should be faster also. Yes,
Under 10 iterations probably,
under
right?
10 iterations. Yes, the only time taken here is because we want a convection model for the ducts. So we
Yeah.
calculate the heat convection inside the duct. So that's what takes time. Otherwise, this is pretty quick calculations.
Yeah. Yeah. And faster for isothermal ground surface, just for
Yes,
demonstration purposes. But
yes.
maybe you can also once that's done, we can just quickly show the result. We don't need to compare with anything, and then
Yeah, yeah.
maybe
We'll show the mesh plot
we'll
as
look
well.
at the mesh plot. But I think right now we can perhaps look at any more questions that have come through. I think we've answered all of the questions, and you guys have been helping each other as well in the chat. If you have any outstanding things that you would like to discuss with us, I think Edston's going to show the mesh plot. If you have
Yeah,
any,
so the results are here. We have all the results here. It's 334 amps for that circuit in all these installation conditions. I'll create a mesh plot. The mesh plot take a bit of time because we have to plot all individual points. So if there's any questions that we can answer, I think there was one question, Jayson, that I wanted you to look into. One is like load factor. For solar and wind farms, are there any typical load factor values that we can use? And how can we calculate load factor?
I think what load factor is pretty standardized, pretty typical for solar applications that we've seen. What around 0.4. With solar, it's virtually on or off. And you can easily calculate load factor using a spreadsheet. You can use our software, has a simple load factor calculator. I think in the next release, we're also improving that load factor calculation soon again. So yeah, it's that's simple to incorporate into the calculation. You can change the load factor, right? It's the settings for each of the circuit. Even they can have
Yes.
separate load factors, right?
Yes, we can have different load factors. Yeah. Another question is regarding the critical temperature rise for soil dryout. Um, like, how do we calculate it? How do we get that value?
Yeah, there's a whole field of related to soil drying. So uh, we use a simple two-zone method. And that critical temperature, what do we know about that critical temperature? Typically it's what, 50 degrees?
Yeah, 40 to 50
Yeah, 40 to
is,
50 degrees.
yeah.
It's a little bit standardized. There are some in-depth technical articles on our website. If you just go to Google and you Google advanced soil drying, you'll find a detailed article on that topic, which explains the two-zone method and the critical temperature, etc. Let me just I'm just getting the link for the certificate. I'm going to
Yeah.
paste paste the link in the chat where you can fill out a form and get an attendance certificate.
Okay, so this is posted. This is the mesh plot that you see here. One peculiarity of the mesh plot is to reduce time, what we have done is we have seen that the mesh is very fine near the edges. This is because edges are the points where there is transition in properties. So just to reflect those transitions in properties, we have meshed them very fine. But as you go far away from the mesh plot, you see that the triangles becoming larger. So this is done to save some time and to reduce computation burden on your machine. This is also suggested by TB963. So if you go to the document, they have some suggestions on meshing, which is one of them is this. We have parameters which you can customize your meshing if you would like to. For example, the minimum edge length is kept to a millimeter. So if you see here, there are triangles which of 1 millimeter edge length. The maximum is 10 meters. So if it's going outside of the soil, very far away from the soil, you can have larger edge lengths also. This is pretty standardized. We don't recommend playing around with this too much because it will waste time in computation, and you won't see much of a difference in your results also. So these are some values that we have pretty much fixed on for all the installations.
We've done quite a bit of experimentation over the years. We've been doing FEM calculations for a number of years, 4 or 5 years now, since our first release of FEM. And we've done a lot of research and experimentation on the meshing, and we think we have a good compromise, a good mesh, and you'll see very little change or difference in adjusting those parameters. So we recommend just leaving them. So I've shared the link where you can get a certificate. I think we've managed to answer quite a lot of questions. If anyone has any further questions, Edson, is there anything else that we would like to demonstrate or discuss? Do you have any other questions that we didn't cover?
I think we are good, Jayson. We are good. If there are any questions, just let us know. We are happy to answer it. Just you can email our support. We will send the email to us the chat, so you can contact us if you have any queries regarding this.
Okay. Thanks everyone for your time.